Hey guys, I'm Tony Bechet, your Physics 2C SI, and let me check this recording. So I figured I'd do something a little bit different for this week. Instead of just going through the slides like I usually do, I'm going to talk about the the um, the concepts that are in the worksheet that I have for this week. So it's kind of like two birds with one stone. So what I'm just going to do is I'm going to read each question, and then I'll go through the concept that you need and the thing that you should be thinking about as you're trying to solve these. Um, this week isn't too bad, but I tried to include everything that was in the three lectures. So whatever I missed, we can go over in the Zoom sessions. So let's get started. Question one. Find the intensity of a 35 decibel bass wave um, produced by a speaker. So with every question, you need to figure out what's important and what's not. So the only thing that's really important is this part right here, 35 decibels. And what are you trying to find? You're trying to find the intensity. So there's an equation for this. Um, the equation is um, no, 10 times the natural log of the intensity that you're looking for and the intensity for the threshold of hearing. And this is a known constant. No, you guys could find this in the slides, but so this is basically what you need for the first one. So let me erase this. Okay, so the second one. Um, describe the difference between a phase difference, and a path difference. Which values will give a wave exhibiting constructive interference? Which ones will give a wave exhibiting destructive? So the main thing to keep in mind with phase difference and path difference is that the phase difference, so let's say we have two speakers. It's a bad speaker. That and another speaker here, like this. So um, you guys are familiar with phase constant and whatnot. So the phase difference is going to be where it starts. So if this started here, with this portion of the wave, but then this one started here, there's a phase difference, as you guys can see, between this and this. And then a path length difference. Um, a path difference can include a phase difference. So if this was, for instance, shifted here, this distance will be the path difference right there. This will be the path difference. Um, what else can I say about this? The key with this is you need to figure out what a wavelength is. So um, the first thing you should ask yourself is, what is the wavelength? That will help you figure out whether it's constructive or destructive interference. And there are specific there's specific uh, ratios where it will be constructive and destructive. But the thing to keep in mind is if we have a wave such as this one, um, when the crests are aligned, we'll have perfectly destructive interference. So they will cancel each other out if we put it together. And then if we have a shift where it's like this is going to be constructive. So usually the phase difference will be the phase difference will be pi over 2. So if there's a pi over 2 phase difference, you will have destructive interference. Okay. Let me just leave these up here. So, number 3, an unfingered guitar string is 0.7 meters long and is tuned to play the E note. So, the questions: what is the speed of the wave on the string? So, so the equation to keep in mind here is the one you saw in Monday's lecture with frequency equals the node and V over 2L. So the reason we're using the closed end equation is because a string is, it has two nodes at the sides. When you use the open and closed end equation, the wave will have a node and then an antinode. So it'll look like this. And I have a question at the end that will cover this, so I won't go too in depth. And then we have another question, part of number 3. How far from the end of the string must the finger be placed to play A above middle C? So this first harmonic is 330 hertz. The frequency is 230 hertz. And then this one that we want to find is 440. So I don't want to say too much without giving away the answer, but yeah, I think that's enough for you guys to know what to do. But basically, where your finger is will be a node, and the thing to keep in mind is, so let's say arbitrarily your finger goes right here. The n in this equation is not referring to the number of nodes. It's not. That looks really bad. It's referring to the antinodes. So always keep that in mind. Okay. So a tuning fork, number 4, a tuning fork of frequency 440 hertz, 440 hertz, is sounded at the same time as a guitar string. Okay. If 6 beats, if 6 beats are heard in 3 seconds, excuse me, what is the possible frequency of the guitar string? So the equation to keep in mind is, so beat frequency is the difference between two frequencies. It's kind of like that beat sound that you hear when there's two different things playing. So the equation to keep in mind is F1 minus F2. But the important thing is there's an absolute value. So because there's an absolute value in this equation, this can either be over or under. It can give the same magnitude of the value. So that's why the key in this equation is where the possible frequencies, as in more than one. So number 5, and just if I don't cover these, if anyone feels like I don't cover these enough, please email me and we can go way more in depth for all of these. So on a cello with the largest linear density equal to this, the string with the largest linear density is the C string with a linear density of this. The string produces a fundamental frequency of 65.4 hertz and has a length of 0.8 between the two fixed ends. Okay, find the tension in the string. So this is related to this one right here. We know that to to this equation right here. So let me just copy this over. So the thing to keep in mind is what does velocity equal? So we're trying to find tension. Is there an equation that relates tension and linear density? There is. So what we can do is use this equation where the velocity of the string is equal to the tension force in the string divided by mu, which in this case is going to be the linear density. So yeah, this is basically just plugging in and figuring it out. So not too bad at all. This one requires a little bit more thinking. So this has to do with wave interference. So draw the resultant wave at t equals 1, t equals 2, t equals 3, t equals 4. It's difficult to imagine things at first, but the more you try, the easier it will become. So the what I'm gonna do is draw this out. I'm gonna draw this out and then move them along. Oh my gosh. Okay. We'll say that's the first one, and then we can say this is the second one. Okay. So basically what you're going to be doing is you can't figure out this type of question without knowing what the velocity is. So the velocity is just one of these grids per second. So this one moves to the left, this one moves to the right. So what you basically do is just in your mind, or you can write these out. Push this one to the left, and then for this one, push this one to the right, and then add up the result. Actually, yeah, no. So this would actually be the resultant wave. Yeah, so this one would be the resultant wave. When it moves again, then we're going to have to, then we're going to have to sum up the different heights. Okay, number 7. So this one is very similar to number 6 or number 4. So a string with a frequency, so my bad, just ignore this one. It's supposed to be number 4. So a string with a frequency of 442 hertz is sound with the second tuning fork of question. With the second tuning fork of question of this one right here. Okay, so for number 7, I'm gonna correct this, but just ignore this right here. This is not needed for this question. So a string with a frequency of this frequency is sounded with the second tuning fork. What is the frequency of the second tuning fork? So it's the same concept. We're going to be using this equation to figure out. So 18 beats are heard in 3 seconds. Keep in mind exactly what a frequency is. So we want this to be in frequencies. A frequency has units of 1/seconds. So that is going to, so you're going to have to do some type of computation with these two to figure out what the frequency is. Make sure the units match. It's 1/seconds. Okay, so last question for number 8. Let's see what this says. Sketch the standing wave pattern of a resonating object that has a fixed boundary on one end and a free boundary on the other. Okay, so closed on one end and then open on the other. Okay, so the length of the resonating object is 90 centimeters. Okay, let's write that on the side, 90 centimeters. Um, and no, this could be a resonating sound waves in a column. Okay, so that's not too important. So what equation we have to keep in mind when we're thinking of open and a closed end, excuse me. What do you have to keep in mind? So it's going to be this equation. So the thing with this one is that the nodes, the n can't be even. The n will not be even if the number of nodes are even. Um, so let's try this with the first harmonic. So let's first draw the diagram. So how do we get one node? It will look like this. This is the only way to get one node, right? Let me change colors. Here we go. Okay. So, what do we have to keep in mind with the number of waves? And what does the number of waves mean exactly? So, um, another way to think about this is how many of these will make up one wave? How many of these will make up one wave? Um, so let's try to find out. Um, this is still half. This is one and a half, and then this is two. So we have um, 1, 2, 3, 4. So this is 1/4 of a wave. Okay. So with wavelength, it's kind of the same thing. So we know that the length equals 1/4 of a wavelength. Okay. So then we know that the length is 90 centimeters. Let's convert this to meters. So this is 0.9. So then the wavelength will equal 0.9 times 4 meters. So yeah, and then do these for the next. So again, my office hours are Tuesday and Thursday from 2 to 3 p.m. We can go way more in depth on this. I just didn't want this video to be too long. So good luck studying for your midterm, and best of luck to everyone.